Okay, so in class we left off with tension force. Let's go to friction force. And the symbol for that we have up here is FR for friction. And it's the force exerted by a surface as an object moves across it or makes an effort to move across it. So here we see that the direction of attempted motion is to the right, along here. But we can see that there's a friction force here which is resisting that motion. And this resistance comes from the fact that these two surfaces are not smooth. They're not perfectly smooth. You can see some jaggedness on that surface. You can see some jaggedness on the surface of the ground. And because of that, the molecules of the box are going to be colliding into the molecules of the surface. And that collision ultimately can make those atoms start to move faster, which makes it heat up. So because the box is being tried to be pulled to the right, we can say that there's going to be a friction force to the left. So we can draw that as a force diagram, and we can label it force of friction of the floor on the box. And another example would be car tires gripping the road as they spin. So there's also another force going on to the next one, force of air resistance. And this, sometimes people call it air friction. But air resistance really is the fact that this object that's moving, like this car, as it's moving through the air, it would have to be pushing the air out of the way for it to go through that air. And that's going to slow down or resist the motion of the car. So you can kind of imagine that we have these molecules as the car's going along. Here, the car, these molecules are going to have to lift up. They're going to get deflected by the windshield. And so that force of the air against the windshield is going to, number one, slow down the car. And number two, it could actually make the air heat up and the surface of the windshield heat up. So air resistance often does cause heating of the surfaces. And an extreme example of that would be a shooting star, where you have a little, oftentimes just a piece of rock the size of a grain of sand, but when it comes into the atmosphere, it's pushing the air out of the way, and the collision between the air molecules and the surface of that grain, that piece of sand, causes the sand to get very, very hot. So if we draw this at the diagram here, we can see that we have the force of air resistance of the air on the car, A on C. And as the car moves forward, the air resistance force is going to be in the reverse direction because it's a resistance. Other examples would be a soccer ball moving through the air. You can think about that or the soccer ball is going to be slowed down also as it's moving through the air from the air resistance. Okay, so I'd like you to try the matching pairs, and I'll be able to see your results on my end. And then when you get through that, the field forces, so this is the other type of forces. We have contact forces, which require touching, and field forces, which don't require touching. So examples are gravitational force, magnetic force, and electrostatic force. And here we can see that these magnets are able to suspend themselves due to their magnetic repulsion. So they're not touching, and that's what makes magnetic force a field force. The one field force that we'll discuss today is gravity. So gravity force, often also called Fg, is the force of attraction that exists between any two masses or objects. So we have this girl holding the bowling ball. And what are the forces acting? So how can we show the gravitational force acting on the ball? We can show it as a downward force. And we can call it force G of the Earth on the ball. Another example would be the Earth pulling on the moon. So in a similar way that the Earth is pulling down on that bowling ball, requiring her to hold it so it doesn't fall. In the same way, the Earth is pulling down on the moon, which is much, much, much farther away and much, 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 much bigger, but still that force of gravity is essentially the same. I mean, it's the same type of force, different magnitude. So for the little final slide here, so going back to the boys pushing the football sled, what other forces can we add now? Originally, we started off by saying that we have an applied force, which is the boys pushing it. And we could also add in now that there's going to be some friction as they're pushing on that. We can point out that there's going to be gravitational force pulling down, but there's also a normal force of the ground pushing up. And we can see that some of these forces are balanced. The upward force of normal force and the downward force of gravity, we can assume are balancing each other out because we don't see the sled accelerating upward or accelerating downward. But the way that we drew these forces for the horizontal, we showed that this force applied is stronger than the force of friction, which would mean that as these boys are pushing it, it will likely be changing speed. If it's not changing speed, then we would assume that these forces are balanced. That's going to be another lesson in itself. So for two practices here, we'd like you to do the draw it. And this first one is draw a force diagram of the forces acting on the basketball. So just imagine, be the ball. You're the ball. What do you feel as pushes or pulls acting on you? And in a similar way, if you're a pendulum bob, be the bob. So the bob is the part that's swinging back and forth. It does not include the string. If you were that bob, what would you feel pulling or pushing on you? And can you draw and label those forces as a force diagram? So one way that you could start is by just putting a dot and then drawing the forces from there. That dot, again, represents the object. And similarly here, that dot that you put in represents the basketball. And then from there you can draw the forces, whichever way they go, either up or down or whichever way. Okay, guys, thank you for tuning in, and we'll go over your answers in class tomorrow.